Let me show you how to be a good Bayesian. Change your predictions after taking information in.
You've also worked something that's called data fusion for US Navy applications. So that sounds very mysterious. How did Bayesian statistics contribute to these projects, and what were some of the challenges you face?
Yeah, unfortunately, I didn't know Bayesian stats at the time. This was when I first started working. But data fusion's actually, we should have used Bayesian stats. If I was to work on that problem now, it should be done with Bayesian stats. The problem in a nutshell, if you imagine you have an aircraft carrier, it can't move very fast, and what it has is about a dozen ships around it. All of them have radars, all of them point at the same thing. If you're sitting on the aircraft carrier trying to make decisions about what's coming at you, what to do next, if there's a single plane coming at you, that's one thing. If all the 12 ships around you hit that same thing with the radar, and it says that there are 12 things coming at you because things are slightly jittered, that's bad news, right? So if they're not identifying themselves. So the whole problem is there enough information there where you can accurately depict what's happening based on multiple pieces of data?
Yeah, that sounds really fun. And indeed, lots of uncertainty. So, and I'm guessing you don't have a lot of data. And also it's the kind of experiments you cannot really remake.
Yeah.
For sure, Bayesian stats would be helpful here, I'm guessing.
Yeah, it's always the edge cases that are tough, right? It's if the plane or the ship that's coming at you says who they are, identifies themselves, and follows normal protocol, it's an easy problem. Like, you have the identifier, but it's when that stuff's latent, right? People hide it intentionally. Then you have to worry about what's going on. The really cool thing there was the guy I worked for, Clay Stanek, had come up with a way to use the Fourier transform of images of each of the radar pictures and just stack them on top of each other. And if you do that, if you see a high intensity, then it means that the pictures overlap. And if there's no high intensity, then it means the pictures don't overlap. And the nice thing is that's rotation invariant. So it really just helped with the alignment problem because everyone's looking at the same picture from different angles. And
It's super interesting also. I love that. And you haven't had the opportunity to work again on that kind of models now that you're a Bayesian expert?
Nope.
Well, you've heard it, folks. If you have some model like that for Daniel, feel free to contact him or me, and I will contact him for you if you want. Actually, I'm curious in general, because you've worked with so many people and in so many different fields. I wonder if you picked up some common misconceptions or challenges that people face when they try to apply Bayesian stats to real-world problems, and how you think we can overcome them.
Yeah, that's an interesting question. I think working with Stan, the common error is that we don't build our models complex enough. They don't describe the phenomenon well enough to really explain the data. And I think that's the most common problem that we have. The thing that I use the most, that I get the most mileage out of, is actually putting on either a measurement model or just adding a little more complexity to the model, and it starts working way better. In pharmacometrics specifically, I remember we started asking, how do you collect the data? What sort of ways is the measurement wrong? And we just modeled that piece and put it into the same parametric forms of the model, and everything started fitting correctly. Cool. We should do that more often. I think if I was to think about it, that's sort of the thing. The other thing is, I guess people try to apply Bayesian models to everything, and it's not always applicable. I don't know if you're actually going to be able to fit a true LLM using MCMC. I think that would be very difficult. So it's okay to not be Bayesian for that stuff.
That's interesting. So nothing about priors or about model fitting or about model time sampling of the models?
No, they're all related, right? The worse the model fits. So when a model doesn't actually match the data, at least running in Stan, it tends to overinflate the amount of time it takes. The diagnostics look bad. A lot of things get fixed once you start putting in the right level of complexity to match the data. But MCMC is definitely slower than running optimization. That's true.
Yeah, I'm asking because as I'm teaching a lot, these are recurring themes. I mean, it really depends really where people are coming from, but you have recurring themes where it can be a difficulty for people. Something I've seen that's pretty common is understanding the different types of distributions. So prior predictive samples and prior samples, how do they differ? Posterior samples, posterior predictive samples, what's the difference between all of that? That's definitely a topic of complexity that can trigger some difficulty for people. And I think that's quite normal. I remember personally it took me a few months to really understand that stuff when I started learning base stats. And now with my educational content, my goal is to decrease that time for people so that they maybe make the same mistakes as me, but they realize it faster than I did. So that's the objective.
That's really good. So what other things do you see that people are struggling with, or do you have, what are some of the common themes right now?
Priors a lot. Priors is extremely common, especially if people come from the classic machine learning framework, where it's really hard for them to choose prior. And actually something I noticed is two ways of thinking about them that allows them to be less anxious about choosing a prior, which is one, making them realize that having flat priors doesn't mean not having priors. And so the fact that they were using flat priors before by default, classic OLS regression, for instance, that's a prior. That's already an assumption. So why would you be less comfortable making another assumption, especially if it's more warranted in that case? So basically trying to see this idea of priors along a slider, a gradient, where you would have the extreme left would be the completely flat priors, which lead to a completely overfit model that has a lot of variance in the predictions. And then at the other end of the slider, extreme right would be the completely biased model, where your priors would basically be either a point or completely outside of the realm of the data, and then you cannot update, basically. But that would be a completely underfit model. So in a way, the priors are here to allow you to navigate that slider. And why would you always want to be to the extreme left of the slider? Because in the end, you're already making a choice. So why not thinking a bit more exhaustively and clearly about explicitly about the choices you're making? So that already usually helps them to make them feel less guilty about choosing priors. So that's interesting.
Yeah, absolutely. And so go on that point a little bit. That's what I'm trying to say with the complexity of the model. If we just assume normal things a lot of times, but sometimes things aren't normal. There's more variance than normal. So making something a t-distribution sometimes fixes it. Just understanding the prior predictive, the posterior predictive draws, also summarizing those, looking at the data really helps. One thing for anyone trying to do models in production, one thing to know is that models, the programs that you write either in PyMC or Stan, the quality of the fit is not just the program itself, it's the program plus the data. If you swap out the data and it has different properties than the one that you trained it on before, it might actually have worse properties or better properties. And we can see this with like non-centered parameterization and different variance components being estimated in weird ways. If you just blindly assume that you can go and take your model that fit on one data and like just blindly productionalize it. And it doesn't quite work that way yet, unfortunately.
For sure.
Let me show you how to be a good Bayesian. Change your predictions after taking information. And